Good morning, students. Mr. Carver here. Today is section 4.4, the first fundamental theorem of calculus. All right, here's the wording of the first fundamental theorem of calculus. If a function little f is continuous on the closed interval AB, this is an x-axis interval, and big F is an antiderivative of little f on AB, same closed interval, then the following is true. The area underneath the function f of x dx over the interval from a to b is equal to the antiderivative of f evaluated at the upper limit b minus the antiderivative of little f evaluated at the lower limit of a. This, people, is the shortcut you have all been waiting for. The left-hand side before section 4.4 required you to set up a summation process with the sum of an infinite number of infinitely thin rectangles. Again, this does the same thing as we talked about in section 4.3. This is the width of every single one of those rectangles. This is the height of every single one of those rectangles. This then is the shortcut. So just like back in the day before we learned about product, quotient, and chain rules for derivatives, we were forced to use the limit process. It's the same really with area. When we started this process, we were forced to use the limit process. Now we've moved into the shortcut, and that's where we're at today. All right, let's work a few examples. At the first example, the integral from 1 to 2 of 2x cubed dx. Again, that's area. It's area because it's a definite integral. It's over a finite interval along the x-axis from 1 to 2. First thing I'm going to do is take that constant out to the front, just as if I were deriving, and that is then the integral of x cubed dx. Recall that the formula for integration is power plus 1 over power plus 1. So I've got the constant out front, x to the 4th over 4, which can reduce to x to the 4th over 2. Now, here's the way the notation works. I switch from the antiderivative with the integrand from 1 to 2, and after I've integrated it, I then use a right-hand bracket, which tells me that you have integrated it and you are now ready to evaluate it from the over the interval rather from 1 to 2. And as the formula states in the previous screen, I take the upper bound and I plug it in, and I take the lower bound and plug it in. Whoops. And I subtract the two in that order, which is going to give me 16 over 2, that's 8, minus 1 to the 4th is 1, that's a half. The answer is 7 and a half. And that actually is the sum of an infinite number of infinitely thin rectangles, just using the shortcut. Now, one question. What happened to the c? There's a couple of ways to look at it. First of all, if I did have a plus c in here, just do it in green. Well, remember, it would be that integral evaluated at the upper bound minus the integral integrated at the lower bound, and the c's will in fact cancel. The explanation I prefer, though, is that this is a definite integral, which is area. You don't need a c. We're actually calculating the numeric value underneath the curve from 1 to 2, as opposed to having an indefinite integral, something like this, just the antiderivative of 2x cubed dx. This doesn't give you area, it gives you a family of functions, right? So this would be x to the 4th over 4 plus the vertical shift of c, either upwards or downwards. C is required here because it's an antiderivative or a family of functions. C is not required here because you're actually getting the numeric value of the area. All right, let's take a look at this example. The same prohibitions, even though we are learning the shortcut, the same prohibitions still exist. That is, no products, no quotients, no quantities other than x raised to a power. This is a quotient, so what I'm going to do, just like I did in section 4.2, I'm going to take this and move it to the top. That's x minus 2. That's times root x dx. This, however, is a product, so I'm going to distribute. This gives me the area from 1 to 4. Same base, you add the exponents. Excuse me, this is incorrect. I need to change this. This is actually x to the negative 1/2 since I moved it from the denominator. When I distribute this out, I get x to the positive 1/2 minus 2x to the negative 1/2 dx. And now I'm ready to go. Integrate each one of them. The first one, x to the 3/2 over 3/2, that is 2/3 x to the 3/2 minus, that's x to the 1/2 over 1/2, copy dot flat, that gives me 4x to the 1/2. Again, evaluated from 1 to 4. I take the upper bound 4, I plug it in, that's 2/3 times 4 to the 3/2 minus 4 times 4 to the 1/2. Antiderivative evaluated to the upper bound, minus then the antiderivative evaluated at the lower bound. And then I take these one at a time. Remember, the 2 is a root, the 3 is a power. Second root of 4 is 2, cubed is 8. That's 16/3 for that first part of the first section. Minus then, I've got 4 times 2, that's going to be 8. Minus then what I get in the second set of parentheses, that's 1 to the 3/2 power, that's just 1, that's 2/3 minus 4. So let's get a common denominator. This is going to give me then 16/3 minus 24/3 minus 2/3 minus 12/3. This gives me negative 8/3 minus negative 10/3. The answer is 2/3. All right, lots of practice with fractions in this section. Incidentally, there was a property that I showed you that said if you integrate from a to b of f of x and you get something like d, if you switch those from b to a of f of x, you get negative d. I think you can see that since this is a subtraction problem, order certainly matters, and if you reverse them, you get the same number with a different sign. That's why that property holds. All right. All right, guys. Section 4.4 is filled with theorems and formulas. And the next two that I need to talk about are the mean value theorem for integrals and average value. All right. Now, if you recall back in chapter 3, we had a mean value in that chapter as well, which is why you have to have this qualifier here. That is the mean value theorem for integrals and the average value. So let me start off with a picture, explain what's happening, and then I'll tell you where the formula comes from based on that explanation. All right. Let's say I've got something that looks like this. I got an f of x decreasing curve. Let's say I'm going from some x value a over here to b. All right. I don't like the way that looks. From a over here to b. The black area from a to b, assuming that this is f of x, is, of course, the area contained between the curve, the x-axis, and my two upper and lower limits along the x-axis. Now, it's kind of a thought experiment, but if I take this area and I reconfigure it so that it's rectangular in shape, so I sort of somewhat squeegee it down and reshape it, I might get something that looks like this. That's supposed to be a rectangle. And so the idea is that this area here, this green area, actually can smash into that area right there. Now, if I take the same area and I just reconfigure it into a rectangular shape, then I think it stands to reason that the red rectangle is equal to the black area underneath the curve. And that's where the formulas come from for the mean value theorem and the average value. Now, if I write out that formula, what I get is the integral from a to b of f of x dx. That is, in fact, the black area underneath the curve above the x-axis between a and b. We know that that's equal to the area within the red rectangle. Now, if you think about the area within the rectangle, it's just base times height, the base of which is going to be b minus a. That is the distance along the x-axis. So let's say this is 1 to 5. It would be 4 units long. And then it is some function tall. Now, before I get there, let me just point something out. The height of this rectangle is f of c, we'll call it. This then corresponding value of x is c. The height of that rectangle again, is just f of c. The height is the average value, and the corresponding x value is what they're asking for in the mean value. So I've got the average value and the mean value. Regardless of what I ask you to solve for, this will be the formula that you're going to be using. And if I take a look at this portion right here, the f of c, again, is my average value, and just my value of c in there is my mean value. So if you start off with the blue boxed formula, regardless of what I'm asking for, it'll work every single time. They're actually stated as two separate formulas in the textbook. I think that's a waste of time. If you can just build the blue boxed formula, you're good every time. So let's work through an example. All right, something like this. The book will ask you to find the average value of f of x over an interval from 1 to 4. They're going to give you that formula there. And again, we just go back to the picture I had on the previous screen, right? The fact that the black area is equal to the red rectangular area. So the black area is nothing more than the integral from 1 to 4 of 3x squared minus 2x dx. According to the first fundamental theorem of calculus, I'd have to integrate that, plug in 4, plug in 1, and subtract them in that order. But before we get there, we're going to set that equal to then the area of the rectangle. And the area of the rectangle in this case is going to be 3 units wide. It goes from 1 to 4, and f of c tall. That is the blue boxed formula on the previous screen that we just talked about. Now, if I'm looking for the average value, really all I'm looking for is this portion right there. Left-hand side is numeric. The 3 is numeric. I can divide through the area by 3, and I get the average value. Let's do it. All right, so the first thing I do is anti-derive. Power plus 1 over power plus 1, and I do them separately. Gives me x cubed minus x squared. Evaluated from 1 to 4. This is 4. That's the wrong color. I want to go 4 to the third minus 4 squared. All of that minus 1 cubed minus 1 squared. This gives me 64 minus 16 minus 1 minus 1. Good morning. That's not 0 minus 0. It's 1 minus 1. That's not 1. That's 1. That gives you 0. This is equal to, of course, 3 f of c. So it looks like I'm going to get, what is that, 64 minus 16, that's 48. That's in red again. I keep switching colors. That's 48 minus 0 is equal to 3 f of c. Divide by 3, that means my f of c is going to be equal to 16. This is, in fact, the average value. All right. Now, if I ask you for the mean value, what I'm looking for is the corresponding x that gives me the y value of 16 on the point machine. So what I'm going to do is make a little room here, and I'm going to plug 16 for my y value and set it equal to my original point machine. It's a quadratic, so I'm going to first take the 16 to the other side. This gives me 0 is equal to 3x squared minus 2x minus 16. Use the quadratic formula. I can factor. Let's go ahead and factor this. I'm looking for 8, so that's plus 2 minus 8, I believe. That's 3x squared plus 6x minus 8x, yes, negative 16. Now I can t it. That gives me 2x values of x is equal to negative 2, and x is equal to 8/3. I'm only looking for the 1 in this interval, which means I can get rid of my 2, and my value of c, the mean value, is actually 8/3. All right, my people, that should be enough to get you through most of the homework. May have some questions. Some of these get a little tricky algebraically. I can certainly help you with that next time I see you. Thanks much.